Welcome back. And I'm pleased that so many people came back. Very interesting. So, we discussed the origin of the threat of today's security infrastructure, which is factorization and elliptic curve based, because Shaw's algorithm can compute discrete logarithms, and discrete logarithms allow us to compute periods, and because elliptic curve based and factorization based can be reduced to period finding, Shaw solves this kind of algorithm with crashes basically in today's infrastructure. And the rescue is lattice-based, and I introduced lattice-based geometrically, and then we move to, okay, let's get a bit more complicated. We need modules, the points of which are tuples of polynomials, and not really polynomials, but residue classes of polynomials, right, to make it more interesting. And now I come back, I come to two famous algorithms that are standardized by NIST with two others. These are the workhorses of the future infrastructure the world is currently building, dilithium and Kyber. By the way, if you are, it's not Star Wars, what is the other sign? Huh? Star Trek, right? The Star Trek is no dilithium and Kyber, right? These are terms they have from there. So, we go back to this learning with error problems. Learning with error problem. So again, we have this ring here, right, of residue classes of polynomials, the coefficients of which stem from this finite ring here. And it's a subset, so the module is also called RQ. This module is part of this Z to the power of k times n. I take a k cross k matrix over this very crazy ring here, so the module of tuples of polynomials, and the vector, the components of which are tuples of polynomials, I take small vectors, right, S and E, and the learning with error problems, as a reminder, meant to solve this linear equation. And this is equivalent to, I take the matrix A, concatenate it with the identity matrix, add a column minus C to it, and then if I multiply it with SE1, I get 0. And we said before, if the integer solutions of this kind of a linear system build a lattice. That means the solution of this equation build a lattice. That means learning with error, in fact, is a lattice-based problem. Right? This is why it's lattice-based cryptography. Now Kyber. Kyber is used for encryption. So Kyber is a lattice-based problem. The standard says I have this ring. The degree of the polynomial is 256, and the prime number q is this here. And it's an art to determine the numbers n and q. You must be a security specialist in order to determine the parameters very certainly, because they control the computational effort behind these algorithms. So I take the matrix A, the k cross A matrix, and the vector, and Kyber is using small dimensions, 2, 3, 4. Why? We'll get clear in a couple of slides. The matrix that I choose and the vector becomes the public key, and I choose, or you choose, a secret S, which is your private key, and a small vector of the error. Right? And Kyber, in order to crack my secret key S, needs to solve this equation to recover my secret S. That means, and you can prove that this vector is also the shortest vector in the lattice here. So this algorithm Kyber that I'm going to describe is the shortest vector problem. Step by step, how does it work? Only the impression. There won't be any test later on. So the private key is my vector that I chose here. It's the private key, and k is the key size. the private key, so the polynomials that I choose in my private key should be small. I explain why. Small coefficients from ZQ. And the public key is AT. A is this kind of a matrix. The matrix is randomly generated. The entries are not necessarily small. The error vector is randomly generated, small coefficients. And then I compute this T, and A got published as the public key. And then when I want to encrypt the message, for each encryption, I generate randomly an error vector, E1, small coefficients, a vector that's called the randomizer, and a single error polynomial. It means a number, what number small coefficients. Each message, the bits of which are B0 to Bn-1, are represented as this polynomial. I scale it, as I said before, by the smallest number close to Q divided by 2. Again, the coefficients are now 0 or this number, and then I compute U, which is A, public key, randomizer, chosen, error, chosen, and I compute T, randomizer, chosen, this is the message. And the encrypted message is this pair. Very strange why. Yeah?
I'm somehow missing the S in the whole slide.
So that's missing?
The secret key, I mean, don't you need the secret key to encrypt?
Yeah, no, the secret key is for decryption. Yeah. This is the public key. I have a message, I use the public key to encrypt the message, send it to you, you use your secret key to encrypt it. Here's now the secret key S. So you receive the V and the U, you use your secret key, which is a vector, you multiply it here, then you get a message M prime. M prime typically is not M, if you compute that here, but it has some noise. These are all vectors with small coefficients. This is only noise, a little bit disturbances. Right? The coefficients are 0 or Q divided Q over 2. The noise has small coefficients. And what I do now is, if I have this M with noise, I round it. There's a function round defined to round it. All coefficients that are close to Q divided by 2 are set to 1. All coefficients that are close to 0, or equivalent close to Q, because Q is congruent 0, are set to 0. And this rounding mechanism, although the rounding is a bit more complicated, then results in the original message. But there is some failure probability, right? Because rounding not always results in the original message, but the failure probability is very short. So here are the numbers that got standardized, right? And then there is a very deep theorem, a theorem that determines the error of rounding based on the dimension of the module and the degree of the polynomial, right? And these are 3 combinations that got standardized, and the error are quite small. That means it rarely happens that a message cannot be recovered, right? And this is the reason that I can't do it. You must be a security specialist in this domain to determine the number so that the recovery error is very small, right? And this is the encrypted message. This is all what I said before. And the rounding mechanism, so rounding works because this is here the error, and because the error is very small, the rounding mechanism nearly guarantees that you only get rid of the noise and recover the original message. And Kyber is used as a key exchange mechanism, so it's substituting Diffie-Hellman, right? So you use Kyber in order to establish a symmetric session key so that you can then exchange messages reliably. Color by example, I only go very shortly. It took me about 2 weeks to compute that. Because if I say this is equal this, remember this is computation modulo Q, you must compute residue classes. It was terrible because I wanted in a simple example, I computed one, I could recover the original message. So I recomputed it again, I got a completely different result. I computed it again, I got a completely different result. The 4th attempt, after nearly 2 weeks, worked. I never touched it again. I don't know whether I'm right or wrong, but it works. So numbers here, so what I do is, we choose a polynomial of degree n equals 4, the prime number is 7, so we are working in this ring here. The private size is q, that means my secret is this vector here, this is my private key. Right? Then I chose randomly this matrix here as part of the public key, and the second part of the public key is computed at this equation with a small error. The error was this vector here. Then I compute t, and I got out this as a public, as t as a public key. So this is the public key. Remember that in practice, n is 256, and not only 4. Right? Manually, you can't do polynomial division of a polynomial of degree 256. It's impossible. So then I use really, it's all Greek to me, right? This is the sequence that we saw before, right? I only wanted to encrypt the first letter, right? Which is 1001. That means the message is meant to this polynomial. This one corresponds to the coefficient of x to the power 3, and this one, as the zeros are this thing. So this was my message. This is the first letter of the message. Right? And if you scale it by q divided by 2, 7 divided by 2 is 4, yeah, 3.5, rounding up is 4, so this is the scaled message. In order to encrypt it, you need to choose the randomizer, the error vector, the error polynomial. This is what I assumed, what I tried. Then you compute these things here, right? Remember, this is all taken modulo 7 and modulo this polynomial. So the u vector is this. You do the same with the v vector, you compute it, right? And this is this vector. Finally, the encrypted message is this pair of vectors of polynomials. This is the message, this got sent around. So, and remember, after 2 weeks, I hope this is still true, because now I decrypt the message. Well, here's my secret key again. You compute n prime, and prime is this what comes out. Then you need to compute it again, modulo 7, modulo x to the power 4 plus 1. You get this message out. If you round it, this is close to q divided by 2, that means 4. It is mapped to 1. This is close to 0, because 6 is close to 7, modulo 0. So I get the same polynomial that was encrypted. Right? But again, it sounds easy. In the past, people took a slope, right? And this is what I did. Yeah. Okay. So then this is an encryption mechanism. There's also something standardized for signature. It's called dilithium. Dilithium is using the same auto-like structure with a different prime number. Here again, as before, you took your secret, the private key, right? You took matrices and compute this thing here, it's the public key. And dilithium has 3 security levels that correspond to different values of m and k. And this is what dilithium has chosen, or the crypto specialist in this domain. And then what you do is, if you have a message mu that you want to sign, you choose again a vector, random chosen vector r1 with small coefficients. You'll multiply a with r1 and round it according to the algorithm that I have described before. Then the standard defines a hash function, the hash function to take the message, concatenate it with the vector w. W is the rounded result of here. Right? This is something called c, and c then becomes part of the signature. And c also, the second part of the signature is this vector here that is computed this way. And why? Because the security gurus say this is how you need to do it in order to be able to verify the signature. Right? And this hash function psi that I've shown before is basically based on something called SHA-KE, and these are variants of the SHA function that we use these days in security infrastructure. And why does that work? So you have, let me go back. In order to encrypt, to sign a message, you need to compute this W, you need to compute this C, right? You need to compute this R2. Sorry. And what you now do is A is part of the public key. R2 got computed in the process of signing message. C got computed as part of the signing process. T is part of the public thing. And the claim is that if I round this here, then I get the original signature back. And this works because here is our small vectors E and C, and rounding is not affected by small vectors. So this basically says rounding helps me to recover my original signature. So the details are irrelevant. Right? Only what is the lithium. So the lithium basically says you have this part of the public key. This is your secret key. What you need is you have your signed message. You concatenate this with the result of this computation, right? You hash it, and this is then again learning with error problem. That means this dilithium thing is also based on the hardness of the learning with error problem. So now we can read this. This was the last mathematical slide. So what's happening in the industry? Industry awareness. First of all, why should you care today? Why should you care today is, look at this, what comes up here. The principle called harvest now, decrypt later. What's currently happening is people are stealing decrypted data like hell. They store it somewhere, because if there's a crypto-relevant computer around, they decrypt it and ask for my value. Right? Very simple. That's currently happening. Right? So many data and are secret and have to be kept for many years, and they are encrypted with today's methods, and they can be cracked in foreseeable future based on a quantum computer. And encryption based on quantum technology requires new hardware, as I mentioned before, that we are building in Europe and China and US infrastructure, extremely expensive, right? And the guess is that only military and government organizations can basically use that. They are protected by quantum communication. But we poor guys, if we go to a bank, go to the online banking, right, we rely on kyber and dilithium that are presented today. So what we need is, we need quantum safe procedure. And if we need them, if we use them, we need to change our software infrastructure. We need to inject somewhere new encryption algorithms, and this infrastructure takes many years. Some of you still remember the Y2K problem, year 2000 problem. There was a significant investment to change the color in the database from 2 digits to 4 digits or even more. This is nothing compared that you have to carve out all your encryption algorithms everywhere and substitute it by post-quantum algorithms. So even this is a significant investment that we need to make. So then that basically means we need something that we call post-quantum cryptography, PQC, sometimes called quantum safe, quantum proof, quantum resistant. It refers to cryptographic algorithms like the lithium kyber, which, according to today's knowledge, important are secure against attacks with the quantum computer. Right? Well, there's no miracle happening, but the crypto specialists come together and basically say these are the best algorithms that we know. Let's standardize them. But they may be cracked by a quantum computer, even by a classical computer, in the next couple of years or decades. And I'll come back to that in a few minutes. But there is no guarantee that these methods cannot be cracked at some point in time, by quantum or even classical computer. So the US government woke up, one of the first government, in 2022, about 1.5 years ago. They came up with a US law that basically says that all government organizations must present a plan within 12 months how to migrate their crypto infrastructure to post-quantum computing. It's a law. And there is a law in preparation that the CEO who does not work on post-quantum computing, and if data is stolen, the CEO is guilty. This puts a threat on that, right? So it's taken absolutely seriously. The European Commission woke up a couple of weeks ago, they said, oh, Jesus, this is complicated and critical. And they recommend to start a coordinated implementation roadmap for the transition. So we are years behind. Years behind. Right? But at least the EU is also working on it. Right? They consider it, they recognize the problem and begin working on it. Industry. In industry, there is a certain kind of awareness that some people heard about it, but we don't have money, we don't know what the implications are, so half of the people heard about it, but they are not really using something. Right? This is a very nice report. Everything can be downloaded for free, right? It's less than a year old. Right? It contains about 80, 90 of this kind of points and the diagrams that you have here. And this shows, if we are talking to CEOs, this slide is a wake-up call to them. So it's called Mosca's inequality. The quantum physicist called Mosca who invented this nice figure. So T-collapse is the time that until vendors will have a crypto-relevant quantum computer available. Right? Maybe some people say 5 years, or optimistic people. Some others say 10 years. My gut feeling is 10 years. There are even quantum physicists who say they will never have a huge quantum computer. Right? They are very pessimistic guys. Right? What I found out is if you talk to quantum physicists, they don't believe in quantum computing. So my suspicion is they want to get money from gathering more research money to make it while industry is just building it. Right? This is why I'm always laughing. So collapse time is the time until we have a crypto-relevant quantum. Migration time is the time your company needs in order to change your infrastructure to use quantum-relevant post-quantum algorithms. And T-shelf is the number of years your information must be kept secret. Right? So you start migrating now. It takes you a couple of years. In the meantime, while you migrate, you produce data that must be kept secret for T-shelf. Even in the last minute, you produce data that must be kept secret for this time. And IBM and INQ and others, they work on quantum computers, and they need T-collapse in order to build a crypto-relevant computer. And if this sum is bigger than the larger than the collapse time, you are in deep trouble. Because then all the data that you produce in the meantime can be cracked. Harvest now, decrypt later. Well, the time you have for migration, dear CEO, is collapse time minus shelf time. Right? Shelf time, if you are naive, you assume that shelf time is 10 years. Most companies need to store the data longer, secret. For example, health data must be stored for decades. Right? If you have a quantum computer ready in 10 years, that a bunch of quantum computing people say, right, your migration time is 0. Dear Mr. CEO, if you have the infrastructure running, you are already in jail.
That if maybe T-collapse is a formula 10 years and you have to shelve it for 20 years. So your migration time is minus 10 years, right?
Absolutely, yeah, sure. You already lost. You already lost. And this is, and then they say, well, why am I in jail? I said, take a look at the US, they're preparing a law where you can be sued, and you know the EU, they will follow, right? And then they get nervous. Right? So this was interesting. So we all know TLS, I don't need to go through TLS, right? TLS. It's a, okay, and we all know Diffie-Hellman. To prepare that. So in TLS, you have a built-in algorithm, very simple quantum number generating algorithm to agree on a secret key. Diffie-Hellman made it more mathematically secure, more secure. And now what's happening is if you change TLS to go beyond the built-in random number handshaking at the Diffie-Hellman, you can plug in Kaiba and other algorithms, you can make TLS quantum safe. And because HTTPS is not a new protocol, but is simply HTTP on top of TLS, you can make HTTP quantum safe. by fiddling around with TLS and plugging in, for example, Kyber. Right? This would be a nice approach to become quantum safe.
And this is fast, right?
Pardon?
To change this.
Yeah, absolutely. I will come to it. It is hard, but it's affordable. I just want to point out. So what are people doing? So the way to become quantum resistant, let's see the classical security algorithm Q, a corresponding post-quantum. So this is Diffie-Hellman, and this is dilithium, for example. Then you can start and substitute the classical algorithm with the quantum algorithm. So instead of using the API that invokes C, you invoke an API that invokes Q. Yeah? Or you replace C by C plus Q. That's the strategy. That means you use C and Q in parallel. You sign your document in parallel with the classical algorithm and the quantum algorithm. Why would you do that? Because this allows you to gain trust into the new quantum bullshit. I don't believe in quantum, but everybody says I need to do it. Okay, I do it. But the classical algorithm I trust. Or you do C before Q, that means you sign with quantum, and after that with, and other combinations are first C, then Q, and other combinations are possible. Here's okay, you have the message, it got signed classically with elliptic curve DSA, and this message got signed by dilithium, right? This is what you could do. But that's not that simple, because post-quantum algorithms have large signature sizes. I'll give you a little example later on. It involves excessive processing, partially. It requires large public and private keys. It requires operations that are often asymmetric between sending and receiving side. And sometimes you have a sender and receiver, that means you need to implement two different mechanisms, right? And so on. Don't dive into the details, because the details, so it's not just a drop-in of a new algorithm, but it's more. And you find 3 documents on the internet. Here are the links if you get the handouts, right? This is from NIST. This is also from NIST. There are 4 publications, right? They describe how difficult it is, and they sketch some paths, what you need to do in order to become post-quantum safe. And standardization is going on. So NIST has an effort called PQC, Post-Quantum Cryptography. Here's the website. And it's a process to submit, evaluate, recommend, and standardize post-quantum safe algorithms. They started 8 years ago, 2018. And the 2 workhorses are Kyber and dilithium. They stem out of crystals, and crystals is cryptographic suite for algebraic lattices. This was work that was going on before. They standardized it, and then they said, okay, the algorithms we evaluate next is Bike, Classic, McEllen, and so on. And I said, so once they published it, what are the next quantum safe algorithms that are getting standardized? Within 1 hour, a team published an article on Archive that shows how to crack this quantum safe algorithm. Yeah. So this may happen anytime. So it's a Hase Eagle. Now there are people who claim I have a fantastic algorithm, and the others are waiting and say, wow, now it's got published. I will toss you, here's the algorithm how to crack it. Right? Well, published standards, published means they have been published in August, and now it's a public process where you can review it and so on. Right? So it is Kyber, we discussed it, dilithium has been discussed, and here's links plus another digital signature algorithm that they can have. So, and this is, okay. And there was an algorithm published to solve the learn with error problem in this algebraic stuff under certain conditions. Luckily, these are not the conditions that Kyber and dilithium assume, but there are already people who work on Kyber and dilithium. Okay, Stefan.
This has been proven to be wrong.
Say again?
This algorithm has been proven to be wrong.
Perfect.
Like you
So-
also learned a few weeks later.
So we are safe for now. Yeah, okay, good. ENISA, close by, they have a nice document where they summarize what is the current state of the world to move towards quantum safe. What others are doing, only selection. AWS, Amazon. Amazon is working on making their products quantum secure, quantum safe. They have products like Key Management Service, KMS, Certificate Manager, Secret Manager, and they offer TLS endpoints that support Leymann and Kyber. And they document what they did in this document. They have a secure file transfer, right? And they have post-quantum crypto TLS with their Key Management Service API. So the details are irrelevant, only Amazon is working on that, right? Microsoft. What I learned in reading through all the stuff is Microsoft has a compute center in the deep sea in front of Scotland. Right? They do it for energy saving because it's cooling for free, and they have a post-quantum secure VPN, so their computations from Redmond to this compute center is very protected. Right? And they have SSH already made quantum safe, and here is what they basically do. They document everything, because this is still work on algorithms that are under inspection. Google claims in this blog here, every internal communication is quantum safe. Yeah? Well, they change everything. The internal communication is quantum safe, and nobody can find out what they are basically doing. They address store now, or harvest now, decrypt later attack by this thing. They are very careful because they first use this algorithm, HRSS, that is also quantum safe, but their IP status is unclear. But the standardization process that NIST is driving is also taking care about patents, so that you are not running into IP issues that Google had. They use something called New Hope, they're quantum safe, in their Chrome implementation, so they removed it because of IP issues. And now NIST is taking care because of the standardization process that you don't run into problems with patents. And since Chrome 1.16, Chrome is quantum safe. If you communicate with Chrome and Google websites, there's quantum safe communication. They use Kyber and elliptic curves. Here you see that different curves are standardized. This is famous elliptic curve. And what you need to do is you go to Chrome Flags, search for Kyber, click on Enable, start Chrome, and then your browser is quantum safe. Yeah, so they take it serious. But you, dear CEO, you don't take it serious. Yeah? Cloudflare is some cloud provider. Microsoft is working with them. They also have a cryptographic suite that they call Circle. Right? They support lithium and Kyber. It's under BSD3 clause license what they do. They applied this to TLS 1.3. And they have a product called Cloudflare Tunnel. And this implementation, this product is also made quantum safe. IBM. IBM has quantum safe support for their key management and transaction support. Data exchange between the cloud and the computer is quantum safe. They have a product called Key Protect that is lifecycle management for encryption keys. It's also quantum safe, so they also take it serious. I myself work with the company WSO2. What we did over the last couple of months, we made their products API Manager, Identity Server, their programming language Ballerina quantum safe. So Ballerina, Sandiva was already there a couple of years ago. This programming language is quantum safe. If you write programs in Ballerina, they can't be cracked. The messages are exchanged. And all of the implementations you saw here and up to now are based on an open source library called libOQSL. Apple developed it. They have a quantum safe implementation of their messaging system, iMessage. Okay. WolfSL is a famous implementation of SSL. They also have a quantum resistant kernel available, quantum resistant MQTT. Some of you are interested in IoT, so they have a MQTT quantum resistant implementation in the open source. And there are also application standards. Here's only one, like X9. X9 is a standard from the finance industry Leymann have a version of their standard that shows how to use post-quantum algorithms to make the financial industry quantum safe. So they take it serious. And most of this happens in the open source. So there is something called OQS, Open Quantum Safe. It's an open source project that prototypes quantum resistant algorithms. Their main deliverable is libOQS. It's an open source C library for quantum resistant cryptographic algorithms. And they integrate the C functions also in what they call applications, so in TLS, in SSH, in SSL, and so on. And there are a bunch of contributors like Amazon, IBM, Microsoft, Cloudflare, Intel, Cisco, and a few universities. They all contribute with OQS. So it's an open source available, and we at WSO2 use this open source implementation. And by the way, just to let you know, we measured no performance impact at all. Zero. It was the same performance when we used the quantum resistant implementations and the classical one. No, zero impact. And we make extensive. So here's a more formal consortium, PQCA, Post-Quantum Cryptography Alliance. The same guys are in there. And the Open Quantum Safe is one of the projects of these companies. They are supporting it. This libOQS, as I said before, is an open source C library under MIT license, although they use subroutines that may have other licenses. So those of you from the industry need to check what the algorithm of the aggregate basically is. There are wrappers for C++, for Go, for Rust, Java, .NET, and Python. Right? They have a little bit less performance. APIs have been defined to these algorithms so that you can host the library somewhere, use the APIs, invoke it. They are multi-platform on Linux, macOS, Windows, on different hardware. They have been verified with different compilers. And the algorithms include Kyber and Dilithium, but provide even more. And the post-quantum algorithms have been used to make TLS, SSH, X509, S-MIME quantum safe. And another ENISA document shows what they did in order to integrate the available libOQS algorithms in their applications. For example, I only go briefly through it, right? We used the Open SSH that was made quantum safe. Open SSL is available for free, quantum safe. And then there are so-called OQS demos, that means curl is available, quantum safe. VPN, HTTPD, interestingly, Nginx is quantum safe. Envoy is a famous sidecar, is quantum safe. Mosquito is also IoT, using IoT. HA proxy is also a web server that we use for scaling. It's also available in the open source as quantum safe implementation. I know what I do. I know the mistake that I'm doing. I'm clicking on a link without knowing it. So, dilithium, yeah, I want to get, here's for example of the Kyber API. What you see here is the piece of code, the C code that uses the keygen function in C in order to generate a key, right? So it's just simple. You just invoke it and you have the key available. Computing the signature, you just invoke the sign method from libOQS in order to verify the signature. You only invoke, what a surprise, the verify method. Right? So it's very simple to use. Here are the different key sizes that you have. Right here, the different security levels, 512, 700. The key sizes are non-trivial. Right? I will give you an example here. Here's an example. If you use classical elliptic curve cryptography, right, the key sizes are 32 bytes, and here they are a couple of hundreds, 1,000, 1,200. This is the key size. So key size changes significantly. Okay, I mentioned that APIs, compile time. So as we saw, the algorithms that are standardized, that are implemented in the open source are secure because our best crypto specialists say there is no attack against them. Right? We saw that, for example, SITE got immediately attacked. Right? It has been withdrawn from the standardization process. The result is you have to be agile. It's called crypto agile. Crypto agility means you must protect yourself against failures of the crypto infrastructure. So if an algorithm is cracked that you rely on, post-quantum algorithm, you change it immediately. The impact is if you encrypt it before documents based on the cracked key, you are in trouble. Yeah? You have a migration path to do. You must unload all the data that got encrypted based on this broken algorithm, and must encrypt it with another algorithm. Right? Whenever an algorithm got cracked, you have migration to do. So an agile infrastructure may look like this. You have an agile cryptographic infrastructure. You have RSA here in. If you follow C plus Q or C followed by Q, you have IASS in it, dilithium, Kyber, and the other algorithms that are currently under standardization. Right? And then you use this algorithm in a round robin. One document is encrypted this way, the other this way. Right? Then you are secure. And at some point in time, if AES is cracked, for example, you can extract it. You need to migrate the data, but then you are still protected. And this is why this NIST effort, post-quantum cryptography, is an ongoing effort. It's not an effort that started 2016. That's end this year, but they are rolling out new and new and new algorithms because they know that people would like to crack the standardized algorithm, and you have a constant stream of new algorithms that could be implemented in order to stay quantum safe. And there is also in the open source something going on that's called Sandwich. There's a company called Sandbox AQ. They have a product called Sandwich, and Sandwich is an open source prototype for an agile infrastructure that you can play around with to stay quantum safe. So this is what I basically go on with. Which brings us to the summary of today. Summary is the infrastructure we have today relies on the hardness of discrete logarithms. Quantum computers will be able to crack this infrastructure midterm, leaving out what midterm basically means. Lattice-based cryptography seems to be rescued. Standards are going on in the area. They are rolled out for post-quantum security. Except for big players, right? Industry awareness is lacking, or if companies are aware, they really don't work on it. Open source prototypes are available. And quantum safe infrastructure must be agile. That means this is also a lot of research that must be done. How do you use such an agile infrastructure? How do you do it best? The summary is this here, as always. So I'm absolutely scared. I worked on this subject for a year now, and I'm absolutely nervous. Yeah, because not much is happening. Right? The most serious thing I see or read is from China. They have geostationary satellites, as I said before. They connect the major cities in China via laser that go to the satellite and back to the other city. So internal communication or government communication is already going on quantum safe. And we are just beginning it. Right? We have this QCI effort going on in Europe, where individual countries are building a quantum-based secure infrastructure. So this is a threat. And I hope that I won't be suffering from this heart attacks. So thank you very much for listening. I don't know how late.
Perfect.
And Johanna, picture. So we have a question and answer section if you like, and otherwise we need to go outside for a joint picture, because experience shows that tomorrow not only a lot of people are here. So questions, except for that we have time at the coffee break. Michael.
Thanks. How do you see in your product what's the chances to integrate the processor as well?
Which process?
Well, the processor.
A processor.
What you're describing is essentially making the data communication more and more secure.
There are already companies that are building appliances. They are building appliances, that means software, hardware bundles for post-quantum crypto.
Because if I was to have your line,
never
in the line.
Yes, sure.
right?
So there are people that are building it. Companies are building it.
So this means we have to change the complete infrastructure to make it really safe.
If you want to make it absolutely.
And then the way of computers, how they work, has also not changed, right? Because the computer scribing is a complete different in that manual room. It's not. So you have to operate in an encrypted space. Otherwise, you're
So what the crypto coprocessor sounds like? Yes, you can do that. I'm not aware of people that are doing that. Yeah? No, we have crypto coprocessors for classical encryption, for example. Yeah?
This is what I would be worried most about.
Yeah.
When you basically touch it at the end and the beginning, but not in between.
Yeah, but if I'm in between of the communication line.
If you're in a encrypted space,
Yeah.
well, you send communication from A to B, and then you process it.
Yeah.
Right? So if I want to
Yes. Yes.
inspire it, I'm not going to.
If you compute, what you're saying is you compute in the cloud, where everybody can go. Absolutely. Yes. Yes. You need to rely on a cloud provider.
The vulnerability is different. So you are talking
On the line, yes, installing.
and you are talking on when it's decrypted.
Absolutely. Absolutely.
In a system that is open, you still have
Some secure coprocessor that we have for classical computing.
Already in 2011, each one used to be system, but we never basically did it when the message was encrypted. We always used text
Decrypted.
at the beginning.
Yes. So my humble answer would be the very same happens today with classical encryption, because only few people use secure coprocessors.
Exactly.
So quantum doesn't make it worse. Okay. Okay. Next question.
For quantum safe TLS, we also need to have a secure symmetric algorithm, and if I understand you correctly,
No, symmetric is simple. The attack on symmetric is brute force. And the quantum way to have a brute force argument is called Grover. Grover has a quadratic speed up, right? And that basically means you need to double the key size in order to maintain the security rate you have today. Yeah, okay, the keys got longer. In this WSO2 work that I do is we need to change the database because the key has a certain length. Yeah? But it is some migration effort, but you can do it.
so we can just use IAS with double key size. And
Yes.
Okay.
No, we're not compensating. You have the same security level that you have today. But if somebody invents a more smart algorithm, you need to double it again, or triple it again. But this, because today's algorithms are brute force based. But it's, let me say carefully, less vulnerable than asymmetric encryption.
So we need to think about
Absolutely.
how much we
And there's research work to do. That's one. Stefan.
I understand that this combination of classical and quantum safe algorithms are central transition.
Yes.
I understand this like a combination of algorithms recommended to make this phase very negatively.
I didn't see it. You know, I'm not a security expert. I didn't see it. I only see C and Q combined, and only for transition phase. Once you company rely on quantum and say, I understood it, it's safe, well, I like it, you can switch off the classical part. Yeah. Yes. Yes. No, I know. I didn't read it. Yeah. If there are no more questions, it's photo time. So we are stop. Here's the question. Whether classical algorithms can So what you're saying is we have this BB84 algorithm that allows to generate and exchange keys. it is supposed to be, no, it is quantum safe, because if you want to crack a symmetric key while it's on the line, you need to copy the key, so to speak. And this can't be done in quantum because there is a theorem called the no-cloning theory. Quantum information cannot be copied without notice. This is why this algorithm is safe. So I'm not aware of any other classical mechanisms to break this infrastructure. I simply don't know it. Everything that cracks keys would be of interest for attackers. I don't see any question. That means let's go outside. We meet back at 2:30, right? After the picture, enjoy your lunch or coffee break or something else. Yeah, have a good time.